at this point, we know everything we need to know in order to do all the programming assignments. The last 2 chapters will be on the final, but it won't be, let's see, won't be too in-depth. In fact, the chapter that we're talking about today, there probably won't be anything on the final on it. This chapter is one of those topics that I think should be taught in 1150 and not held off until 1450. And I don't know why it's held off until this late in the book, actually. But graphs are pretty cool. I probably will ask a question on graphs. So pay attention on Tuesday. I really like graphs. Graphs are pretty cool. Everything is graphs. All right, so today we get to talk about inheritance. The book calls it extended classes, but it's really inheritance. And if you still have, you all used the Liang book for 1150, correct? I know you did, Dion. 2 semesters ago, it's the bird one?
Yeah.
Okay. Jack, did you use the book with the bird on the cover? Let's see. It was red. It looks like this, except it's red.
Yes.
Okay. There are 2 versions of this book. One's comprehensive and twice as long, and one's brief, and we use the brief one. So, let's scroll down to the table of contents. Somewhere down here. Brief contents. Here we go. So, Dion, I think your class got to chapter 8, and that's where you ended. If you still have this book, and I wouldn't blame you if you sold it because it's an absolutely terrible book, but if you still have it, it's not a bad thing because you can refer to stuff in it. Chapter 9 is a good thing to read. And today we're basically going to take chapters 10 and 11, really, and cram them into one lecture. Chapter 14, if I had more time, I would talk about chapter 14 as well, because chapter 14 is one of those things that is, if you don't have that in your knowledge of Java, you are missing something. You can still write Java programs, but this is one of the things that makes Java Java. Chapters 10 and 11, Thinking in Objects and Inheritance and Polymorphism, are 2/3 of what makes Java object-oriented. So, in 1150, you learn 1/3 of what makes Java object-oriented, and aside from that, you basically learn C. Today, we're going to finish that off, finish those pieces of the pie. Talk about the other 2/3 of what makes Java object-oriented, and I definitely recommend, basically don't sleep until you do, is what I'm trying to say here. Read chapter 14, because abstract classes and interfaces are really, really, really cool. We've already used interfaces, and we don't have time to talk about what makes abstract classes different from interfaces, but they're worth learning about, worth knowing, and they're used a lot in the Java framework. So if you end up using Java a lot, you will encounter abstract classes, interfaces, and you'll need to know how to use them and probably how to create them as well. Right, but that's not our book. So, is anyone familiar with the concept of inheritance? Either in Java or in other languages? Java or other languages? Okay. Dion and Lynn, no experience with inheritance? Besides the book, no. Okay. What about you? Any experience with inheritance in any language?
I think I might have. Can you give me like a quick rundown?
The
Very bad with learning definitions from my first course.
idea that one class implements sort of a broader type of things, and then narrower types of things can use that functionality.
Yeah, I think I use that.
Okay, cool. So, the three big main points of object-oriented programming are encapsulation, polymorphism, and inheritance. Encapsulation is sometimes also called information hiding, which is basically the whole concept that we've been using the entire semester. You start learning about that when you start talking about objects and methods to a certain extent. The idea that everything acts as a black box, you expect it to do what it's supposed to do, and trust that it does what it does well, and isn't going to break on you all of a sudden. And that's basically the assumption that we've been using all semester with implementing data structures. We create some type of data structure. We expect it to operate a certain way. We don't care about the inner details, so the information is hidden. There's our information hiding. And it's all brought together under one package. Not package in the Java sense, but package in the wrap it up nicely, stick a bow on it sense. That's encapsulation. Polymorphism should actually be listed after inheritance. But polymorphism is the idea that overloading kind of fits into the category of polymorphism as well. It's the idea that you can have a bunch of things with the same name, and when something needs to happen, the right one is chosen. That's also how the toString method works. That's part of polymorphism. Java provides a default implementation in this general objectness. Things that are objects have a toString method automatically. However, if you implement a toString method, Java will choose that one when you need to use it, as opposed to using the default one. And inheritance. Like I explained very briefly, the idea that we can define a general class of type and then define specific subtypes of that. So we have things like organisms. I think that's actually what the book uses. Organisms. And animals are subtypes of organisms. Plants are subtypes of organisms. Bacteria are subtypes of organisms. Viruses are not subtypes of organisms. Viruses are technically not living, so they can't be organisms. Then under animals, we have things like fish are subtypes of animals. Birds are subtypes of animals. Reptiles and amphibians are also subtypes of animals. I'm missing something. Mammals. Don't want to miss them. Yeah. We don't need to describe the entire animal kingdom. But basically, we get this inheritance tree, this hierarchy. And the reason that the organism, animal, plant, that tree is a good example is because it's a taxonomy, and classes form a taxonomy as well. There are things at the top that broadly describe everything below it. Then we have subtrees that describe everything below them. And in addition to simply being broad descriptions, this inheritance also carries the same idea of inheritance in human terms. When someone dies and we inherit something from them, or even if they don't die and we still inherit something from them, like when we get clothes from an older sibling or something like that, things are passed down. This idea of passing down. So things that are higher up in the hierarchy pass down their internal data, their instance variables. They pass down their instance methods. And without doing any extra work, just by saying a class inherits from another class, and we'll see exactly how to do that in just a minute, we get access to all of those methods. I lost my mouse. Here we go. Before we get into that, I'm actually going to kind of skip over the general topic of inheritance, which is basically the first section of this chapter, where we're not dealing with anything data structure looking, we're not dealing with generics or anything like that. I'm going to talk about visibility modifiers and how they are affected by inheritance, and then I'm going to start using some of this generic stuff in examples using inheritance. So, visibility modifiers. Most of the time, we've used public and private, and for the time being, it was sufficient to say that there were only two visibility modifiers, public and private. Public meant that everything in the world could see whatever was being modified. Private meant only the current class could see what was being modified. We're going to add two more, one of which won't actually be useful, but will be complete. There are actually 4 visibility modifiers. Obviously, we have public and private, which means that exactly that. Public, everything in the world can see it. Private, only this class can see it. We then have another visibility modifier called protected, and that means that only this class and subclasses, so classes that inherit from this class, can see or use this variable or method. There's also a modifier called package, and that means that anything in the same package can make use of the of that variable, method, whatever. And packages were discussed earlier on in the book, so I won't go into detail about them now. The useful one is protected. So one example in particular that the book talks about, which is one of those things that you might not think about until you actually try to use it, is on page 686 and 687. And the problem that is posed is something like this. So here I'm going to create a class called complex, and it's going to inherit from double. That's what this extends keyword means. So automatically, wherever I could use a double, I can also use a complex. And since actually making it operate like a complex number would be kind of outside of the scope of this class, I'll leave it like that. So our imaginary part is always 0. So it's still a real number. So let's save that. Public class inheritance. This is my main class. So if I create a variable of, yeah, I can spell, type double, I can obviously do something like this. That works because of boxing and unboxing. I can also do something like this, which is equivalent. That's actually what Java does when it gets compiled. But I can also do something like that. Because I said that complex extends double. That means complex is a double. It's a subtype of double. So anywhere a double is required, I can also use a complex. Which in terms of math really actually doesn't make sense. It should probably be the other way around. But semantically, we'll throw semantics out the window and just use this as an example. Now, double has a constructor that takes a number. However, right, just save this. Oh, that's fun. It looks like I can't actually extend it. So this means that the constructor is actually private, which means that I probably couldn't even do something like that, because it can't construct a new double. However, that does work. So there is a constructor on double that takes a double. There is no constructor that does not take any arguments. So that means that I have to do something as far as constructors are concerned here. If I'm going to create a new complex, I do need to specify which constructor on double I'm going to call. And so let's start by creating a constructor for complex. Public complex double A and double B. So following the A plus BI syntax, here we'll just call doubles constructor like that. So we pass in a single double, and this keyword super indicates the instance of the superclass. And in this context, since I put parentheses after it, that means call the parent constructor. Try to find a constructor with this number of arguments, number and type of arguments. And that will compile fine, and once we change this back, yeah, okay. Double is final. There's another keyword called final, which basically says you can't inherit from this class, ever. So I can't actually do what I'm trying to do. I should be able to do that, though, because double inherits from number. This is actually the number class requires that I implement a method. It's saying the method double value. I know that it returns a double. So now this is starting to become a very full-featured class. Well, getting there anyway. Double A. Well, those should not be public. Those should be private. And here, instead of calling a superconstructor, because number doesn't actually have that, this dot A equals A, this dot B equals B. Float value. This is probably going to get very irritating very fast. Oh, yeah. Let's try that. Float. Long value. I don't really care how accurate any of these casts are. I just want this to compile at this point. Right, so now I don't have a constructor that does that, so we'll just use that constructor. Right, this is no longer a double. This is a... Okay, so complex inherits from number, so we can store complex in a number. And then we can do number-like things with it. So, let's say we write a method that takes numbers. No, we write a method that takes collections of numbers. So, public static that's always a good one. Let's be very, very generic about it. Both double meaning there. Collection. We want a collection of numbers. And let's actually be use something that we've seen before. Iterable of numbers. So that means we can use the for each loop line, and that each element inside it is a number or something that inherits from number. And here we can do something. The important part is not what we actually do here, it's the method signature and the types and all how that all goes together. So in Java there is something called an array list, which is something that looks like a list and uses an array as its data store. So kind of like the array bag that we implemented at the beginning of the semester, except order is maintained. So let's say array list of number, my list equals new array list It really doesn't matter if I put anything in it for this exercise. We're not worried about what it does when it runs. We're worried about what will make it compile or not. So here, if we call sort on my list, do we think this will compile or not? How about this? Let's step back a minute and will that compile? Small piece of information that might be useful. Arraylist does implement the iterable interface. Dion, what do you think? Okay. Clark, what do you think? Lynn? Jack? Okay, the answer is yes. The answer is no. What did I miss? Oh, I didn't return anything. There we go. Assuming I had all the housekeeping out of the way, it would have compiled. Okay, so yes, the answer is yes, it does compile. So now let's change it back to what I had before, which was this. Will it compile? All in favor of yes. Nobody thinks it will compile. One person thinks it will compile. All in favor of no. One person thinks it won't compile. So I guess you two don't know whether it will compile or not.
We don't take a choice. We can't be wrong either way.
That is very true. You can't be right either. The answer is yes, it will compile. Because really nothing changed from before. The array list that we're creating is still an array list, and array list still is iterable. That hasn't changed. Nothing has changed here. So now let's do something a little bit different. We've said, when we declared complex, we said complex extends number. So complex is a number. So let's start there. Will that compile? The book actually doesn't talk about this situation, so I'm not sure. If what the book says later on is correct, this will not compile. And that is correct. Can anyone tell me why? It is exactly the same reason that's given in the book for a different case. And it has to do with inheritance. So complex does inherit from number, but here we're not trying to take a complex and store it in a number like we are on line 5. Here we're taking an array list of complex numbers and trying to store it in an array list of numbers. Array list is, it's meaningless to say it inherits array list. An array list is an array list, so that's not the issue. But at this point, when it gets compiled, it looks at array list bracket number and array list bracket complex as atomic, well, not atomic types, but atomic names for types. Java says, well, array list of complex does not inherit from array list of number. And really, there's no way for us to create an declare a class array list of number and then declare a class array list of complex that explicitly inherits from number. However, the book says we can do something like that. And I don't actually know if we can do that here. Yeah, it complains. So, in this case, we do have to say not array list of number, but array list of complex. We could also just do that, and let's comment that out. That's the next question. So that works because an array list where the generic thing is specified does kind of implicitly inherit from an array list that is still genericized. An array list is more general than a specific implementation of array list. Questions? So now let's change this back to array list of complex. And the next question is array list of complex, array list is an iterable, and complex is a number. Will this compile? And we already all know the answer to that because I compiled it before, and the answer is, anyone? The answer is no, this will not compile. And this is the example that the book gives. And the reason this does not compile is exactly the same reason as it didn't compile before, is because while array list is an iterable and complex is a number, there's nothing wired up to say that array list of complex is an iterable of number. So the way we fix this is with more generics. And here, that syntax will actually work. What this says is, I am expecting something that is iterable or something further down in the hierarchy. And I missed something somewhere? Oh, yes. I have to say that I'm using generics. Or, yeah, other way around. So, here's where I specified the generic, that I'm using the generic, and here's where I actually use it. So, I am saying I am expecting an iterable over e's, and earlier on I say what e actually means. E is something that inherits from number. So now when I click compile, it works fine. Questions? this is one of those things that you will probably not intentionally use, and you certainly won't go into a project saying, hey, I want to use this crazy generic stuff. Generics by themselves, making a collection that can operate on any data type is useful. We've been using it all semester. But this sort of nuanced stuff, you'll probably never intentionally write it. But when it crops up, it's good to know how to fix it. So with that, the rest of the chapter really is just examples of inheritance and examples of extending other classes, and nothing really pertaining to data structures. So instead of talking about that, section 13.4 talks about abstract classes. So even if you don't have the Liang book, you can read through that and get some perspective on abstract classes. Instead of talking about extending collections that use generics, I'm going to talk about something that I find really cool, really useful, and it's kind of degenericizing something that is a generic. And I actually used this in the compiler design class here. I didn't write mine in Java, so I won't be giving you code, so it's okay. But basically, I wanted to write a symbol table, very similar to the one that we had to write for PA 4 or 5. And rather than do all the work to take one array of strings and one array of ints, or let's see, what was it there? I think it was an array of strings and an array of ints, or somehow put some table together, either keep track of rows or keep track of columns, whatever. I figured, hey, wait a minute. I was writing it in C#. C# already has collection classes that do that. Let me just take that functionality that already exists and add on to it. What is the mechanism by which we take functionality that already exists and add on to it? That is called inheritance. So, a couple of classes ago, I think a week ago actually, we played around with hash map and tree map. So, I'll use tree map. And if I did that, that probably actually would all sorts of not compile. That's going to not work because I already have a symbol table there. Yes. Oh, cannot find symbol tree map. That's different. Okay, so that works fine. The trouble with that is that it has replaced both placeholders with object. So now I have a tree map of objects that maps to objects, which is really not what I'm looking for, not going to be very helpful. However, if I were using a tree map directly in this symbol table context, I would create a tree map of strings to ints. Strings to integers. And I can do the same thing here. So now I have a symbol table class that extends the tree map class, and everything that was a generic is now replaced with either string or integer. So there are no generics here. Regardless of where I use symbol table, it will always be a map of strings to integer. And that will compile. And potentially for my application, that might work fine. However, the programming assignment specification said implement these specific methods. So there was something like add symbol with value or something like that. And that was expected to take the name of a symbol and an int. Not an integer, just an int. And we'll call that value. And now we can start implementing basically the adapter. So we take something that exists in Java that we want to use the functionality of, we extend it, and then we start writing other methods that kind of adapt what we already have to the functionality that we need. Another way we could accomplish this is simply by having an instance variable of symbol table that is a tree map. However, then we'd have to go through multiple layers of method calls. We can't just use anything that's protected in tree map directly. So this gives us a little bit more flexibility. And then we don't have to write methods like add or something like that that just would pass right through to tree map. Or I guess it would be put and get. Those are useful methods. We might want to expose them on symbol table, but we don't want to have to implement them again and simply call off to the appropriate method on the tree map that is an instance variable. Visual Basic, before it became truly object-oriented, the only way of doing inheritance was doing exactly that, which was absolutely horrendous. So here we might do something like if get str so that means if it already let's see, does not equal no. I'm making some assumptions about how tree map works. I don't remember exactly. If get str does not equal null, that means it already exists. Return. Don't do anything if it already exists. Otherwise, I think it is put str. And we get lucky here because ints and integers automatically box and unbox, so we don't have to do anything crazy. Though we could, just to make it obvious, do something like that. Let's make this a little more helpful. And then we can do something like, let's implement a main method right here. Right, that looks like something that will test this. Compile. Uh-oh. I didn't use the right method name. Symbol with value. Now we run it and everything works fine. We also automatically have available to us everything that TreeMap has. So everything that Simple Table inherits from TreeMap, which includes the iterable stuff. So for each right, and we can use ST just like it's any other tree map. All we're doing is specifying a bit more information to it. What does... Oh geez. Java is not C#. For each not applicable to... Is tree map not iterable? Tree map is not iterable. However, it does have a method somewhere in here. That might work. Oh, by the way, when you're writing your own programs, there will come a time when you don't know something. This is an excellent way to find out. What can I use? What is there? So, let's see what key set gets us. It gets us a set. What is a set? A set is iterable. Cool. That gets us what we're looking for. So, dot key set. And that compiles. Cool. Key set is called key set and return to set because there is no guarantee of order with the keys. In fact, a week ago when we were talking about what tree map did, we mentioned that we looked at the documentation and it says this is a red-black tree. We looked up what red-black tree was and it said it is a binary search tree, which means that it does some sorting among the keys. So we can't add things in a particular order and expect that those keys are still going to be in the same order. So since there's no guarantee of order, set is just a collection of things with no guaranteed order, so it kind of makes sense. And it looks, to me anyway, that it does an in-order traversal of the tree. So these keys would end up being alphabetically ordered. We can test that very unscientifically with something like that. Questions about how inheritance and generics work together. Any questions about anything in this region of this method? Does everyone have some direction for the homework assignment that's due today, right? Yes. Yeah, today's Thursday. Okay. Any questions on that? Has anyone started it? Okay. Good. Quick reminder, the last homework assignment, which is due a week from today, is implement 3 parts. Part number 1, implement heap sort. Part number 2, implement selection sort. Yes, selection sort. Part 3, in your main method, create some array of data, or some array of data. Randomly generated, it doesn't really matter. As long as you use the same array, the same values in the same order as the input to both heap sort and selection sort. Then save the current time or whatever it ended up, current time millis didn't give enough granularity. So nanotime or whatever it was. System.nanotime, I think. Let's see. System, not fast. What? System. Use the system.nanotime. Use that method to get the current time in nanoseconds. Run one sorting algorithm, either heap sort or selection sort, on the array, and then on the next line, immediately call this method again to get the ending time. Subtract those two and print out how many nanoseconds it took to run that sorting algorithm. Do the same thing with the other sorting algorithm on the same input array. If you do an in-place sort with either of them, both of them can be in-place sorts, make sure you make a copy of the array first before you call the sorting algorithm. That copying of the array should not be between when you get the time. That shouldn't be part of the time calculation. Basically what you're looking for is to show that heap sort is quicker than selection sort. I recommend making a large array by large, I mean several hundred elements, and populating it using, let's see, M's are northward. Math. This function, math.random, that will give you a pseudo-random, an array of pseudo-random values, and makes it easy to construct a very, very large array. You don't have to sit there typing in seemingly random values. Because you probably won't see much of a difference in the time difference unless you have a large number of elements. With that many elements, you might be able to use system.getTime_millis, but use nanotime anyway, just to, in case your computers are really, really quick. When I grade these, I will not be looking for details too much in the way of printing out two numbers, building an array, sorting them, printing out two numbers. As for the details of that, I'm not concerned. I'm actually not entirely sure how I'm going to grade these because they are due midnight on the 2nd, and I get on a plane at 6 a.m. on the 3rd. So I will probably grade them in the airport. Everything up to that point will be graded because I'll grade the exams Thursday. So the only thing I'll need to do is fill in boxes in my gradebook and submit the grades. So, yeah. I can grade 4 programs while waiting in the airport, the Colorado Springs airport. It's pretty quiet there. All right, any other questions on anything? Cool. That's it for today's class. You're welcome to stay and work on the assignment, either assignment. You're welcome to stay and ask me questions on the assignments. You're welcome to stay and ask me questions on what the exam will be like. Exam. The exam will be exactly like the midterm. Did I already talk about what the exam's going to be like? I know I talked about it in the other class yesterday. The final will be exactly like, same format as the midterm. All short answer. I don't remember exactly how many data structures we talked about, but probably structured something like that into parts. So we talked about trees, searching, sorting, and graphs. So there will probably be a section on trees, a section on, I'll probably group heaps and sorting into the same section. So a section on heaps and sorting, and a section on graphs. I don't know. There might be a section on recursion, then a section on trees. We'll see. There might just be 2 sections, one on recursion and tree-like stuff, and then one on graphs and general data structure stuff. What we learned today, I don't know how to test you on what we learned today, is really the answer. It's either I give you a piece of code and ask you whether or not it will compile, and you say yes or no, and the answer would probably be no, so it wouldn't really be a fair test. Or you'd have to actually write code to demonstrate something. And either situation is just bad. So you get a freebie on that one. Graphs will definitely be on the exam. I enjoy graphs.